Good morning or afternoon, depending upon where you are viewing from. My name's Larry Trager. I'm the moderator for this panel. Interesting, we just went through a last-minute change on the streaming, so we were all worried that we were even going to be able to make the panel, but it worked out fine thanks to our great technical support. So we're really excited today that we have a great panel that we've assembled, and we're going to discuss for the next hour and a half surface power on the moon and Mars as part of our breakout session 1A. I've actually known these panelists for a number of years, and they're all leaders in their respective areas of expertise. Our first panelist is Dr. Ralph McNutt. Dr. McNutt is a physicist working in the space exploration sector of the Johns Hopkins Applied Physics Lab. Ralph is also co-investigator on 4 current NASA missions. Ever since I've known him, he's been an investigator for a mission of some sort. He also worked on the National Decadal Survey team that prepared a report for the Decade 2013 for 2022. He's going to discuss partial history of space nuclear power and the nuclear imperative for Mars. So we'll hold our questions for the end. You can send your questions in, and we'll field them at the end after all 4 panelists speak. So with that, I will turn it over to Ralph McNutt for his discussion. Ralph.
Okay, Larry, thank you so much. Can I have the first slide, please? There we go. So good afternoon, everyone. So what I'm going to do is give you a little bit of a whirlwind tour of some history, because it's always good to know where you came from in order to know where you're going and how you can get there. So we're going to go back quite a few years. Next slide, please. And go back to the beginning, technical readiness level 0. If you go back in astronautics, basically everything was inspired originally by either Jules Verne or H.G. Wells in the modern world. They sort of laid the original ideas about traveling in space from the Earth to the Moon with Verne, and of course the War of the Worlds with Wells. Next slide, please. But at the same time, a lot was going on with respect to our understanding of radiation and nuclear power when it first really came on the scene. And that was with Marie and Pierre Curie, with their discoveries of radium and polonium. And indeed, Marie Curie, the first woman to win a Nobel Prize, and also won 2 Nobel Prizes, one in 1903 with her husband and one in 1911. The others in terms of learning really about radioactivity for the first time and sort of the idea of nuclear power. Marie Curie actually coined the term radioactivity. Next slide, please. And so that led into Konstantin Tsiolkovsky in Moscow and Robert Goddard in the United States. And both of them talked about trying to get outside of the Earth's atmosphere, trying to look at rocketry, trying to look at the ultimate rocket. And both of them actually in their initial writings, Tsiolkovsky in 1911 and Goddard in 1918, talked about interatomic forces and radiation and accelerating particles with electricity as possible ways of getting to advanced propulsion, interestingly enough. Next slide, please. So what one needed, of course, was some way of actually developing the technology, and that really was provided by, unfortunately, the Second World War. The parts for the World War II, of course, were the original operational rocket, the V-2, that was used as a weapon, and nuclear weapons, which were, of course, used as weapons. That transitions, of course, rapidly into the Cold War. One of the first things that happened was sort of a division of power across the globe. There was work that was done in the United States for looking at a reconnaissance satellite to be able to see what was going on in the Soviet Union, all, of course, very highly classified at the time, originally coming out of the Douglas Aircraft Corporation and later, which was folded into RAND. The need was for a 500-watt electrical power supply, and at the time, people saw nuclear as being the only way of going about doing that. Next slide, please. So the other thing that happened was with nuclear thermal propulsion. And again, Most people are not aware of some of the background on that. That was also actually driven by Cold War priorities as well. We had developed the fusion bomb in the United States. The Mike device came in at about 74 metric tons, was detonated in the Pacific. And one of the questions in that test, and one of the questions was, how could you deliver such a thing? And again, this was an operational issue that went back to the delivery of the atomic weapons at the end of World War II. And so that led to thoughts about, well, okay, so how would we go about technically doing this? Next slide, please. And the idea was, well, what one could do, perhaps, was to use nuclear energy itself in order to provide an upper rocket stage. Nuclear thermal propulsion, this is where it came from. Speculations going back to 1946, 1947, looking at the idea of using a nuclear reactor to heat up liquid hydrogen and use that as the propulsion means for being able to lift heavier payloads than you could with chemical rockets such had been developed by Goddard and the others during and before World War II. Next, please. So there were a lot of technical studies that were carried out. Before that, there was a lot of hardware work done. 1942 to 1955, this is the beginning of setting up the various programs. Lots of discussions going on while the things that were developed and fielded, such as the B-36 with more conventional bombs. Problem was how that one could deliver something, a weapon, across something like 5,000 kilometers, or 5,000 miles, excuse me, back in the day. Again, a lot of studies that went on. This continued on up into Los Alamos and the newly established Lawrence Livermore Radiation Laboratory being established, both looking at what one could do with propulsion using nuclear power. What ended up happening was that there was a division between the two, with Project Pluto, a nuclear ramjet idea being developed by Lawrence Livermore, and Project Rover, a nuclear thermal rocket being developed by Los Alamos. Next, please. So there was a Space Nuclear Propulsion Office that was actually set up in 1961. That endured up until 1973. Their main task was to come up with a nuclear rocket engine for nuclear rocket vehicle applications. It was the so-called NERWA program. This is a joint program that was run by the Atomic Energy Commission and by NASA. Harry Finger was the actual head of the office, and he reported both to the commissioner of the AEC and to the administrator of NASA, and everyone else in SNPO reported to him. It turns out that at the same time, the radioisotope power system supply program was also running, and this was also a small part of this office, but mostly this was concerned with nuclear thermal rocket engines. Next, please. So Project Rover, again, started in 1954. It was transferred over to NASA in 1958 because by 1957, the United States Air Force had decided that nuclear rockets really no longer had any sort of a military role. But with the burgeoning of the space program with respect to NASA, it was recognized that they might have a role there. And this is when NERWA was set up, of course, with tests that were conducted on some 24 reactors out in Nevada. This is the Kiwi A test that's shown here. Next, please. And the largest one that was built was, of course, the Phoebus 2A engine. This was actually run for 12 minutes at full power at Jackass Flats, Nevada, June of 1968. 4.4 gigawatts of power, about the same power output as an F1 engine on a Saturn V, but with a specific impulse of around 825 seconds and a liquid hydrogen flow rate through the core of the reactor of about 125 kilograms per second. They shut down after 12 minutes only because they ran out of liquid hydrogen from the tank cars that they had available. Next, please. So multiple nuclear thermal rocket engines were built and tested not only in the United States, but also in the then Soviet Union. A lot went on about trying to work out materials properties of the fuel form, how that one managed to deal with the radiation background for the various pieces as well. And a great deal of technical progress was made, which also cost a lot of money. This was a very large program. Several billions of dollars were spent real year dollars at the time in getting up to this point. Next, please. So at the same time, we were looking at reactors in space. SNAP-10A, which was another piece of what had been originally dealing with trying to get a power supply for reconnaissance satellites, was actually flown, developed at the Santa Susana Field Laboratory in Simi Valley, California. The SNAP-10A was actually the one nuclear reactor of the United States which was flown. It was launched out of Vandenberg in April of 1965. Worked for about 43 days and then had a non-nuclear fault, which caused the reactor to scram as planned. Next, please. So at the same time, we looked at nuclear electric propulsion. Everything looked good, but the trouble is, for all of the developments that went on, there was a problem with the actual mass to power ratio that one could develop with all of the auxiliary pieces. But at the same time, it really was the cost of flight that has been the main deterrent of all of that. For example, the most recent project was NASA's Project Prometheus. The pre-phase A study was estimated the first vehicle cost as being about $16 billion. This was for a science mission, and that was excluding the launch vehicles, and basically was too expensive for what the Science Mission Directorate at NASA could afford for doing something only for the reason of science. Next, please. So radioisotope power systems, on the other hand, found a very important niche within NASA and has been running ahead. We've spent in the U.S. about $4.7 billion, that's an FY11 dollars, developing this technology. We've been using them since then. Right now, of course, we've got a new one, the MMRTG, that's on the Perseverance rover that's on its way to Mars. Next, please. Plutonium-238, of course, has been the key material for fueling those power supplies. The research on that began in the 1950s at the Mound Research Laboratory in Miamisburg, Ohio. Developed since then. Mound actually produced well over 500 RTG units. A lot were used on the defense side of the house. But again, since that, everything now, for the most part, is being used by NASA, currently powering New Horizons, powering the Voyagers, and powering Perseverance and Curiosity at Mars. Next, please. The space nuclear power has remained a major enabler for NASA Robotic Science Missions. These have all been using RPS. Next, please. Robotic missions are certainly expensive. Using these, a lot of these have been nuclear powered. We've spent about $70 billion over about 31 missions across 57 years or so. This is going up until 2015. Next, please. But of course, human missions are even more expensive. Then there are also things that we can think about going out and enabling with nuclear thermal propulsion and with nuclear power supplies. Indeed, enabling meaning that we really have to have them. U.S. has spent about $500 billion on over 57 years on human space flight, so a rate that's higher than that for, of course, the robotic missions, not surprisingly. Next, please. So enabling, of course, means you can't do it in any other way, and it's certainly enabling for operating long-term on the moon or on Mars. Human missions are going to require more than kilowatts of power, as the other panelists will talk about, and really, if you look at it, only nuclear fission can provide that. Next, please. You have to be aware of cheap promises. The good news is that we know the cost, but in some sense, that's also the bad news. Next, please. So the real journey has really only just begun. Next, please. But there's a caveat. One of my favorite quotes attributed to Thomas Edison is that vision without execution is hallucination. One needs the vision to drive us forward, but we still have to be able to execute. We have to worry about what our real requirements are. Those have got to be commensurate with realistic cost estimates and funds. And those really are the key elements of any successful space mission. either robotic or human. Next, please. So the future is up to us. And I just remind everybody the saying by George Santayana that those who cannot remember the past are condemned to repeat it. So we have the challenges that are out there, but I think we're up to the task. Thank you.
Very, very good, Ralph. We appreciate your presentation. You had a lot of slides, and we were all worried you're going to get them in, but you did. So thanks a lot. And I know on each one of those slides, you could probably talk for 25 minutes on each slide alone, but thanks a lot. Our second panelist is Dr. Bhavya Lal. She's going to discuss policy. So Ralph talked about history, the history of nuclear. Dr. Lal is going to talk about policy issues in space nuclear power and propulsion. Dr. Lal is a senior researcher for the Institute for Defense Analysis for the Science and Technology Policy Institute, that's known as SNPP. And it's located across from the White House, so I'm sure she has a lot of fun walking to work when she does go back to work with all the activity there. So SNPP is one of 3 federally funded FFRDCs, research and development centers. Dr. Lal supports the White House as well as NASA. She supports science and technology policy. So with that, Dr. Lal, you have the stage. It's your turn. Thank you.
Thank you, Larry. Ralph is a tough act to follow, but I'll give it a shot. Shout out to my SNPP colleagues who are on the space team, especially Max Butcher, who's my co-conspirator on all things nuclear. So actually, before I begin, I'd like to make an observation. We are talking today about the opportunities and challenges of nuclear power in space. But let me remind you, back in 1933, Ernest Rutherford, the discoverer of nuclear structure of atoms and one of the most prominent scientists of the time, called the expectation of harnessing the power of the atom for practical purposes moonshine. We are talking today about using nuclear power in space. It makes me proud to be living in these times. I'm proud, but we have real work to do. Over the last 65 years, and I think Ralph gave an amazing summary, we've spent many tens of billions of dollars developing nuclear systems in more than a dozen programs. But other than radioisotope systems, which, by the way, remain as expensive as they were in the 1970s, we have, and one reactor we launched in 1965, again, before most of the people who are part of this conference were even born. We have not launched a space nuclear system. Why is that? There are lots of reasons, but one part of the answer is poor policies. I will talk about policies that will affect the future of developing and deploying space nuclear systems. So let's start with policies. What policies exist to guide space nuclear systems? So if I can go to slide 2. So the first thing to say here is that there's really no explicit policy impediments to space nuclear systems. In fact, if you look at that figure on the right-hand side, you will see that space nuclear systems have been of interest since the earliest days of the space age. In a special message to Congress in '61, and again, I may be repeating a little bit of what Ralph said, right after we spoke of funding for the Apollo program, President Kennedy spoke of the Rover nuclear rocket. So yeah, this has been of high interest throughout our history. But if you fast forward to today, the National Space Policy makes specific references in support of space nuclear systems. Last year saw the release of a memorandum on launch approval, NSTM-20, that updates the process for launches of spacecraft containing space nuclear systems. It also, and actually that's pretty awesome, it also establishes processes for commercially developed nuclear systems. Third, again, sticking with the executive branch, the National Space Council document, which just recently came out, New Era for Space Exploration and Development, notes that new options for surface power to survive harsh lunar nights, such as space nuclear fission reactors, will be vital for long-term operations on the Moon and Mars. And more recently, and I think maybe Lee and June may talk about that, DOE and NASA have put out an RFI on developing a surface reactor for the Moon and Mars. Moving to the legislative side, there's appropriations for nuclear systems, nuclear thermal propulsion in particular. The latest bill on the authorization side has 15 references to space nuclear systems. and lots of discussions underway on the development of these systems. So what is the problem? The reality is really somewhat different. If we can go to the next slide. Despite no formal impediments and despite tens of billions of dollars, as I said earlier, we have no systems that are even close to being ready to be launched. So why is that? So I have a few thoughts on that. Up until recently, this is the most important one. No one clearly asked for a space nuclear power or propulsion system, right? NASA never said, for example, we need a propulsion system with an ISBFX, a thrust of Y, and year Z, right? None of that. Even when there is a mission pull, it is often for a Ferrari, not a Ford focus. In other words, we want to skip the incremental development process and go straight to the top of the line solution. Second, there is a lack of sustained investment. Current development efforts are more of a tech push rather than a mission pull effort. And again, the dozen or so efforts we've had in the past were almost always tech push. But these two factors are related. When there is no mission pull, investment is half-hearted, and it is easy to pull a plug when funds are constrained, when priorities change. And because there's no mission pull, investment is weak. And because there's no investment, users have a hard time raising their hand asking for the capability. The key is to break the cycle, and maybe we will have time at the end to talk about this a little bit as a group. The third challenge, and again, it's related to the second one, we like to develop sort of the top of the line nuclear systems, say through DOE labs. Cost effectiveness has never been a goal of our space nuclear development efforts. So this is an area we've been doing a lot of data collection for years. When we talk to colleagues in the private sector, we often hear that they're forced to work with DOE labs that tend to be expensive. Of course, DOE labs need to be involved. They have experienced personnel and facilities, but there's a downside to that. Another component of high costs, outdated regulations that haven't kept pace with tech developments that in principle increase costs. And these regulations are not just outdated, but opaque and confusing for government actors and completely lacking for commercial actors. This has recently begun to change, and I will return to that in a bit if there's time. Last but not least, there are some really complex trade-offs that need to be made between tech alternatives, timelines, costs, and philosophy. For example, how does one decide whether to use low-enriched uranium, LEU, or high-enriched uranium? Both have upsides and downsides. Or whether we'd like to go to Mars with nuclear thermal or nuclear electric propulsion systems. Again, both have strengths and weaknesses. Third, and this is actually an emerging topic of debate, do we need to do ground testing whole hog, or can we do more modeling and simulation and do partial tests on the ground and more testing in space itself? These are all evolving topics. Moving to the next slide. So what are some of the policy issues we need to address as a community? So here's a starter list for you. So at the core, we have the issue of constancy of purpose. Can we pick a target and stay on it? How do we set goals for nuclear systems, ensure adequate funding, and prevent the whiplash of these major starts and stops that have happened over time? How do we ensure that requirements are commensurate with realistic cost estimates and available funds? Second point, private sector is increasingly more competent. What is the role of the government versus that of the private sector? Should the government become a customer only, or stay developer and user like it has been? Would there be cost efficiencies if systems are developed commercially? All of the terrestrial nuclear power in the United States is commercial. Should space nuclear power have a higher bar, or should it be similar enough? A third point, how can commonalities across agencies be leveraged? So both within DoD SCO is developing a surface reactor. And within DoD DARPA, there is development of a nuclear thermal propulsion system. Are there commonalities in fuel development, reactor development, power conversion systems? Would that result in staying on course and cost savings? I mean, the evidence from history is mixed, but it's certainly worth looking at. The next major point I wanted to make was these common needs across agencies. How do we work not just in principle, but at the ground level? Ralph mentioned that SNPO office where the director, Harry Finger, reported both to the NASA administrator and the AEC. How do we do things differently, learning from the past and moving towards the future? As another policy issue that we need to address, even as we're addressing this core issue, is how do we better address environmental and safety concerns during operations, or things like decommissioning in space or on the surface of a celestial body? We currently have no guidance on operating nuclear systems in space. There's no US government agency that has the authority to tell the private sector how to behave in space. Another issue, as Russia and China develop space nuclear systems, is US leadership, for example, related to safety, related to security, innovation, necessary? Or do we want to cede ground in these important areas to players whose priorities may not align with us? And last but not least, how do we address the issue of public perception about the dangers of nuclear power? Let me give you an example. The world went mad when the tsunami hit the Fukushima plant in Japan. Do you know how many members of the public died as a result? 0. Do you know how many died because we were trying to relocate them? Thousands. As a community, we have done a terrible job communicating with the public regarding the risks of nuclear power. That's on us. I'd like to now move on to a couple quick examples of policy challenges I raised. I'll share 2, one where we have begun to address the challenge and one where we hope we'll be able to. Hey, Larry, can you remind me how much time I've got?
Yeah, you got another 7 minutes.
Okay, cool. So that gives me a chance to kind of talk through the 2 examples I wanted to. If you could go to the next slide, please. So the first one is the launch approval process. So it used to be, next slide, it used to be that the process used by the US government to approve these launches was originally developed in 1977 and minimally updated in 95 and 96. There were many different organizations involved in launching a space nuclear system, and there was no one legal or policy document that captured the process completely. As this chart shows, some processes resided in the executive office of the president, the boxes on the top left, others in agencies, if you look at the bottom row, and some of them came from legislation. Next slide, please. This slide kind of lays out the timeline of approval for 4 different missions. And again, none of these are fission because, one, we haven't had a fission reactor launch for since 1965. So the process, in fact, that is one of the major challenges of the previous launch approval process, that there was no way to approve fission systems. But the point to make here is it took between 4 and 9 years to get approval for launch. And there was really no good way to assess ahead of time how long something might take. So there was a lot of conservatism built into the system. If you go to the next slide, please. On this slide, we kind of laid out, and this is a study that SNPP did that consolidated all the challenges in the launch approval process. The first one was that it was expensive and lengthy, and every option every test that you could do to ensure that the requirements or the rules were met were just done. It was perceived as a requirement. There was no differentiation between levels of relative hazard. A small radioisotope heating unit, or what we call the REU, went through the same approval process as tens of kilograms of highly radioactive plutonium. Processes were duplicative and inefficient. There was lack of communication between agencies in important points in the process. And even though the process was generic, it was clear that it didn't cleanly apply for fission systems. And last but not least, as I mentioned earlier, there was no way for the private sector to be involved other than as an agent of the government. So next slide, please. Last year, the government tried to address this specific issue and, working with relevant agencies, developed a process for how space nuclear systems would be launched. One key innovation was a tiering system. The tiers were based on the characteristics of the system, the level of potential hazard, and national security considerations. So now, based on the new process, a spacecraft that is a very, very small amount of nuclear material, such as the REU I mentioned earlier, can be approved without much bureaucracy and at an agency level. And a system that has the potential to expose the public to high radioactivity levels, or one that raises national security and nuclear proliferation concerns, will be approved by the President of the United States. And I have it on good authority that a notional lunar rover with ruse to survive the lunar night will likely save the taxpayer about $30 million with no loss of safety. So there's something to be said about the impact of policy issues on developing nuclear systems, and that was the reason I wanted to walk through this example. Another one, if I could talk through that one, if I have time, and I'll keep it short, is next slide, please. Is whether we use highly or low enriched uranium in our systems. Next slide. So experts, when they discuss LEU or HEU, and I'll just use those acronyms, they're just faster to speak to, focus on one or two issues. Typically performance, those who promote performance tend to prefer HEU and don't talk about some of the other concerns, and those who prefer LEU only focus on the security-related concerns. However, as you can see from the third bullet, it isn't just performance that is a criterion. There is others as well. Safety being one, for example. There's debate on all of these points. Proponents of HEU proclaim that there's greater complexity of many LEU designs, makes it more difficult to preclude inadvertent criticality under all accident scenarios, for example, during launch. However, LEU proponents note that at high power levels, there aren't significant differences in terms of launch safety. Security is one of the core issues when you talk about HEU or LEU. HEU systems present greater security challenges relative to LEU. In principle, the fuel could be conceivably stolen during development, transportation, storage, after a launch, re-entry, or even from space. On the other hand, we really haven't had any, HEU fuel stolen, and the likelihood of that is quite small. There's other issues, fuel availability. HEU is more available in the near term because it's directly obtainable from our stockpiles, whereas producing the low-enriched uranium would require downblending from the stockpile or enriching low-enriched uranium to levels that are required to a level called HEU-LEU, high-assay LEU. Cost is another interesting issue that is raised in this context. This cost of development, launch, and operations, and there's obviously differences between security costs, for example, when you use HEU. My view here is that the cost of a nuclear system would be high enough that enrichment levels will likely not be a major differentiator. Another important issue is public-private partnerships. When you're using low-enriched uranium, the private sector can be much better and more deeply involved. And if the private sector comes with funds, then public-private partnerships may be easier to establish. And lastly, there is a very important political acceptance issue, and it is actually connected with the security one. The United States discourages the rest of the world to not use HEU. However, if we ourselves use HEU, discouraging others from doing so, it may appear hypocritical. And some non-proliferation experts and advocates worry that this might weaken non-proliferation efforts. So my point is, and if you can go to my last slide, my point here is that there is whether we use HEU or LEU is ultimately a political decision, not a technical one, with lots of policy thrown in. I mean, obviously, in my view, it would be prudent that we retain flexibility and allow the use of HEU in space systems, but only where there is mission, which is not possible without HEU, or where HEU is a significant enabler of a mission scope. With that, let me yield the floor to my colleagues, and I'd be happy to answer any questions that you might have.
Yeah, hey, Bhavya, I think we'll hold the questions until the end of everybody speaks, okay?
Sounds good.
Let me go. So far we've talked about history, Bhavya talked about policy, and now we're going to get into the last two speakers. We'll discuss some of the actual technology that's out there and some of the direction from NASA for the future. So our third panelist is June Zakrajsek, and she's going to discuss radioisotope power systems from the extremes of our solar system to our backyard, the moon and Mars. So June is the program manager at Glenn Research Center. She has over 20 years of aerospace systems development and research and project management experience. She manages a very, very big area that we've been talking about today, the whole radioisotope power system program, which ranges from the MMR, the multi-mission radioisotope generator, to the enhanced version, to the next gen, and then the dynamic radioisotope power system. So she covers the gamut. Basically, her most recent RPS system is on the way to Mars. We talked about Perseverance, and it will land in February of 2021. So with that, June, we're looking forward to your discussion.
Thanks, Larry. If you could bring up my charts, I'd appreciate it. And I appreciate being on the panel. And so what I will try to do, if you can go to the next chart, is I'm going to try to talk about how RPS has been involved and what RPS systems are and where we see them going. So RPS, or radioisotope power systems, basically have been providing the power to explore, discover, and understand our solar system. NASA explores to discover the secrets of the universe and to discover those new and exciting phenomena, search for life, better understand our own planet, and to protect and improve life. We can use radioisotope power systems. In many of the NASA missions, given a high priority by the scientific community, they visit some harsh, dark, cold locations in our solar system. And those missions would not be possible or would be extremely limited without the use of nuclear power. And radioisotope power systems being one type of nuclear power, or RPS as I'll refer to it, it can provide that gap and that ability to explore. And so radioisotope power systems, they harness the heat from the natural decay of plutonium-238, and that is what's used to produce continuous electrical power for operating our spacecraft and our science instruments that allow us to explore, discover, and understand. If you can go to the next slide, please. So I'd like to tell you a little bit about how we look at the program and how we implement it. I'm sure all of us understand that as being human, we're really by nature trying to explore and understand. And so we've been using RPS to help us do that for the past 60 years. And I think we can summarize that within the program under 4 areas: people, power, progress, and production. So the people part of it, the RPS program, it primarily supports the Science Mission Directorate, Planetary Science Division at NASA. And we have a very passionate and talented team to work to try to provide the RPS systems and to support the missions that use them. We have a cross-agency and cross-organizational team. We use people at NASA and DOE. We have a partnership with the Department of Energy, and that allows us to look at new systems as well as deploying systems. And we have a distributed leadership team. We have people on our team that help lead the program that are not only from Glenn Research Center, but also from the Jet Propulsion Lab, as well as the Applied Physics Lab and the Department of Energy. A little bit ago, you heard both Bhavya and Ralph refer to the hairy finger timeframe, where we had one organization. We don't actually have it very formalized like that within the RPS program, but we have definitely implemented that philosophy in how we've organized and how our people help support the program. And we do that those people really have allowed us to provide power for difficult and complex missions. What you see there is you see the one system that we have available, which is the multi-mission radioisotope thermoelectric generator, the MMRTG. And that's the one that's powering Perseverance that Larry talked about a little bit ago. It's also powering Curiosity, the other rover that is exploring Mars. And it provides about 110 watts of electricity. And I'll talk about that more in a little bit. But I just want to leave you with that. That is not really a lot of power. And so we do it's because of the ingenuity that we can use just that limited amount of power to explore, to design spacecrafts, and make progress. We make progress so that allows us to move forward with science and exploration. And we also try to move technology forward. And no matter where we are exploring, we're going to need power. Nuclear power is unique. We use solar power a lot for our exploration. However, nuclear power allows us to reach those extremes, to reach those unique areas of our solar system. One aspect of that is the Voyager mission. Right, we use RPS on the Voyager mission that allowed us to reach the limits of our sun's sphere of influence and beyond. And then production. So as we move forward to try to explore our solar system, we need to make sure that we have what we need and the fuel to provide to the RPS systems. And so NASA, working with the Department of Energy, established something that we call constant rate production. And not only does constant rate production help us reduce risks to missions, it's also helped us reduce costs by about 25% to missions. And it also has allowed us to reestablish the capability that we lost over 30 years ago in the United States to produce plutonium-238. And some of that plutonium-238 that DOE has produced is actually powering Perseverance. It is in the heat sources that launched on July 30th to Mars. And so right now what we're doing is DOE is scaling up that production rate to meet NASA's forecasted needs. If you could go to the next slide, please. So here's a look at all of the missions that RPS has powered in the past for the United States, and there's over 25 missions here. And I'm just going to highlight a couple of those. And you can see that these missions have flown by, have orbited, have landed, and have roved on these planetary bodies. But I'm going to talk a little bit about New Horizons mission, and that mission that went to Pluto. It's powered by a single radioisotope thermoelectric generator. Here, what we're doing with a thermoelectric generator is we're taking the heat that's provided by the plutonium-238 and we're converting that into electricity by using thermoelectrics. And that primarily has been the technology, that thermoelectrics has been the technology that we have been using in RPS for all of these missions. And at this start of the mission for Pluto, the RTG provided about 245 watts of power. I just checked last week, it currently is at 184 watts of power. So it does decay in its power as time goes on, and that's primarily because of the heat source characteristics, as well as the thermoelectric that decay. So New Horizons is also the first mission that is exploring the Kuiper Belt. That's a region beyond Neptune. Was discovered in about the 1990s, and it's revolutionized the way we look at our solar system's architecture, formulation, and evolution. The spacecraft itself launched in about 2006. It had a Jupiter gravity assist. In 2007, did some science around there as well, and then arrived at Pluto in the summer of 2015. And the data that we got back from that transformed the way we are looking at that information from that particular system. We learned, not only did we see the heart that everyone is aware of, but we learned that it's really not just the rock. Right, it has atmospheric hazes. Charon, one of the moons, shows that maybe there's a freezing of former water ice ocean inside, and maybe Pluto could have an internal white water ice ocean today. So we're learning things all the time. It allows us to observe, and we would not have been able to do that with solar power. And now the spacecraft, it left, obviously, it left the Pluto system back in 2015 when it flew by, and it rendezvoused with one of the Kuiper Belt objects, Aerojet, which is about 1 billion miles out beyond Pluto. And it allowed us to understand a little bit more about some of these primitive objects and it also is a spacecraft that has had the farthest planetary encounter. If you could go to the next chart, please. And so talking a little bit closer to home, we're looking at the Mars 2020 and the Perseverance rover that I've just mentioned. And it launched on July 30th. And it's there to better understand the geology of Mars, seek signs of ancient life. It's going to basically sample rock and soil and leave those samples so that we can return them to Earth in the future. It's also testing new technology. Again, it has, and you can see it there in the picture on the right, you can see the RPS. It's the object that has the fins that's coming out of it. It provides about 110 watts, as I said before. And so you have this spacecraft that is the size of a small car that we're powering on that 110 watts. And that robotics and the ability to rove is also helping us pave the way for human exploration. It's allowing us not only to better understand the conditions, but it's also being used as a robotic precursor that we can test technology, such as landing technologies, so that we don't have to put lives at risk and we can understand what we have done. We've done that in the past on Apollo. We had missions to the moon that had robotic precursor missions like Ranger and Surveyor, and that allowed us to understand how to better land, where to land, and how to return safely home. And so that's part of this whole Perseverance is the first part of a 3-part process. And in that process, we'll understand better how to leave the surface of Mars, how to rendezvous and dock with a spacecraft around Mars, and how to get back to Earth. All of those things are vital to help support the Mars mission. And of course, we want to learn what is habitable in Mars, what life could have been supported in the past, and what will it take for us to, as humans, to be able to live there in the future someday and visit someday. And so if you go to the next chart, I'm going to talk a little bit about how RPS, what we've been looking at in RPS, and how it also might support the Moon-Mars future for the agency. And here what we did is we studied, I was skeptical that we could find a need besides REUs, and I'll talk about those in a second, to support the Moon-Mars architecture and what NASA is planning on. And so what we did is we looked at the different architectural elements and we said, hey, is there any place that RPS could play? And I was surprised to find out that there are considerations when you compare RPS to what fuel cells could do, whether those fuel cells were on the lander or whether they were on the reactor. What RPS could do if you were using compared to solar cells and fuel cells. And in doing that, we found that there is some goodness to considering RPS for a surface mobility system. And so we're going to look at that and trade that a little bit more and try to understand a little bit more what that might entail and how that might entail. And the reason why this played out, one of the reasons, and if you go to the next chart, that would be helpful, is that the RPS technologies that we were looking at there were based on dynamic technologies. And so it's one of the ways that the program is investing in innovative energy conversion technologies. A dynamic system would have a conversion efficiency maybe 3 to 4 times greater than our current state of the art. But I've got moving parts, right? So I've got to figure out how do I prove out a lifetime of 17, 20 years that could use moving parts. And to do that, we've been looking at, we have things on test that have been on test for the past 14 years to show that they can continue to operate successfully. And we have been looking at how we can develop a system even to demonstrate on the moon so that we can prove that a dynamic system can work through and handle launch, land, and operations, and can continue to operate and support science needs and bring them back. And one thing that I did tell you I was going to talk a little bit more about is radioisotope heater units. It's one of the other areas that we could use to support and survive the lunar night. A power system can provide power, and there is a lot of heat that is also generated that can be used. But if you don't have that, you could also use radioisotope heater units to support surviving the lunar night. The program has been working to try to make sure that those systems are usable and accessible to the missions. As Bhavya talked, with regulations being changed and with working with the Department of Energy, we've considered programmatic NEPA efforts to try to make sure that the use of REUs are more affordable to survive the lunar night for missions, as well as we've looked at safety analyses that would be able to help along with the regulations to make them more affordable as well. And so I think that these systems are within the reach of NASA missions to use for critical mission objectives and critical systems. We also, within the program, are looking at building on the 60-year heritage of the thermal-electric energy conversion and using, making investments. Larry talked about the next gen. It's a system that we're looking at that could have advanced thermal electrics that could increase the initial power, but also the end of design life power that we could supply to a mission. It is a system that is targeted to try to get back what the system is that we're using on New Horizons, a GPHS RTG, because we would like that larger kind of a system to help support our missions. If you could go to the next. And so we are looking at different aspects to help us support not only the science missions, but also Mars and Moon, whether that is with precursor missions and getting science, as we are with Perseverance, but also with developing new systems that can support and help support the vision of our future. And if you go to the last chart. So as we venture from Earth to Mars, as explorers, the power that we can provide with RPS for both robotic and human missions, we think is critical. And so we feel that nuclear power system applications can help with that. I appreciate your time today, and I look forward to talking later and questions. Can't hear you, Larry.
Larry, you're muted, sir.
Sorry about that. You told me to mute, so I muted.
You're wonderful. I appreciate you doing
that. I forgot. I apologize. So the MMRTG, multi-mission radioisotope generator, works in the vacuums of space on the surface of a planet. And if you think about a mission, New Frontiers mission that might cost billions of dollars, the power source is so critical, and the power source can't fail. Otherwise, the whole mission and all the instruments that were built into it will not be available to work. So power is so important. Anyway, we'll get to conclude with Lee Mason, and he's going to put everything together, and he's going to discuss power technologies for the lunar and Martian surfaces. Like all of our panelists, Lee is a nationally recognized expert. He's been working at NASA Glenn for many years. He has over 30 years of experience at NASA Glenn and Cleveland. He's currently serving as Deputy Chief Engineer for Science Technology Mission Directorate. So Lee, you have the floor to wrap up. Thank you.
Great, Larry. Thank you very much. And I appreciate all my colleagues that went before to set the stage for this. You've gotten a heavy dose of nuclear. I'm going to try and put a little balance to it, maybe talk a little bit about requirements and also about some of the power technology options. So if you could bring up my first slide. And one correction, and it's a very common one, but people, when they see STMD, always want to put the word Science Technology Mission Directorate, but we are the Space Technology Mission Directorate. And our objective is to really kind of provide the technologies that enable both the human exploration missions as well as the science missions. So we're really cross-platform and trying to develop technologies that are multi-use. If you go to the next slide, I wanted to introduce you to our big portfolio, and this is a snapshot of what we're trying to develop to support the Moon Mars initiative. If you had the opportunity to hear Jim Ryder speak yesterday, he would have given a much more eloquent explanation of this chart, but it really comes down to the 4 elements that are shown on the bottom. We've kind of broken up our technology portfolio into these themes. They are go, land, live, and explore. And so the go technologies are really about the propulsion systems that will get us from Earth to the Moon and onto Mars. The land technologies are really about things that will allow us to land big payloads on the Moon and Mars precisely and not cause too many issues with the systems that are already there, avoiding hazards and eliminating plume debris. Live is really about establishing a presence, human presence there, and putting all the infrastructure in place so that we can have a sustainable effort there, both starting on the Moon and then eventually onto Mars. And then explore really gets at some of the science mission pools that STMD supports. So not only on the Moon and Mars, but to the outer planets. And we have a very important kind of key initiative that relates to this particular conference. It's called the Lunar Surface Innovation Initiative. And under that activity, we're developing a lot of the key technologies to permit this sustainable presence on the Moon and provide a kind of a foundation for going to Mars. And some of the key technologies that are included in that are things like sustainable power, which we're going to talk about, things like dust mitigation. How do you prevent dust from impacting your systems and in their performance? I already mentioned precision landing. A lot of the missions that we're talking about going to the Moon want to land on the rims of craters. And so how do we do that and know that we're going to do it accurately without causing issues for our payloads? We're certainly working collaboratively with our Science Mission Directorate friends that are developing what's called the Commercial Lunar Payload Services. In fact, that is a forum that we use to demonstrate a lot of our technologies. We already have probably a dozen different technologies that will be demonstrated on CLIPS landers. Cryogenic fluid management is a key technology thrust for STMD. We're looking at how to not only store and transfer cryogens in space, but also how you maintain them on the surface, especially, say, if you mine water from lunar ice and you make it into hydrogen and oxygen, how do you provide that as a resource for landers and other space vehicles? The next one, surface excavation and construction, is an important activity. It builds on work that we're doing in low Earth orbit, looking at manufacturing and on-orbit assembly and leveraging some of those technologies and looking how they might be put to use on the lunar surface. And then finally, extreme access. We know that the Moon and Mars both have very difficult environments, and we are trying to develop the technologies that will allow us to get to the far reaches of those very difficult environments. Next slide, please. So I'm going to talk again about requirements a little bit. So back up a bit, rather than talking about the power solutions, let's talk about what we need. So we see human missions to the Moon as kind of the first step. we're talking about returning humans to the moon in 2024 and probably going to the lunar South Pole. The concepts are that those early missions will be short in duration, maybe 3 to 7 days, and they would, to a great extent, leverage the abundant sunlight that's available at the South Pole crater rims. So we're trying to develop technologies that take advantage of that abundant sunlight. And depending on the seasons, that light might be continuous. And so if so, why not put up some solar arrays and take advantage of it? By 2028, we hope to have a sustainable presence on the lunar surface. And there are kind of two competing approaches that we might consider for that permanent presence. And the first one has to do with maybe establishing a single site that we would revisit on multiple missions with a gradually expanding infrastructure. And in this case, probably a strong dependence on ISRU propellant production. In other words, we'll establish one place on the moon and we'll start making propellant, and we'll use that as a bootstrap to not only expand that location, but use it as a means to get onto Mars. An alternative approach is to have a mobile architecture, and this one's a little bit more complicated, will require a lot more probably autonomy and things like that. But the idea is to land a set of assets and potentially move them between sites and have the crew visit new sites with each visit. So that's another idea that's being explored, and certainly that one gives us a maximum exploration footprint. So both of those are being studied, and we'll see more as those studies materialize. But in general, what we see for the moon are power requirements in the tens of kilowatts for the early missions. And we think that those requirements are going to be heavily influenced by the crew habitats, the environmental control that has to maintain the crew thermal environment through these extreme temperatures that are present on the moon, certainly life support, ISRU, maintaining that cryogenic propellant in its liquid form for our landers will be a key power driver. And then charging rovers that will allow our crew to explore the surface of the moon. I think that those requirements could improve or increase dramatically for large-scale ISRU, but we see that as kind of a longer-term vision. And we know that the temperature extremes on the moon are going to be a big challenge. Next slide, please. All right, so let's talk about Mars missions. We know that we've been successful flying a number of robotic missions to the moon, or to Mars. And we know that those systems are probably don't have the required power sources that we'll need for human missions. In fact, as successful as they are, missions like MER, the Mars Exploration Rovers, Phoenix, Mars Science Lab, and now Perseverance, those are all tremendously important and successful missions, but their power sources were all less than 200 watt. Which is not going to suffice for human missions, which we know are going to require at least tens of kilowatts. There's a number of studies that you can read about in the literature that suggests that the power requirement on Mars is up to 40 kilowatts for day and night, continuous power. The concepts in many cases assume that initial missions will be robotic. We'll deploy assets that will make propellant that the crew will use to get home. But for the first 2 or 2.5 years, it might be completely unmanned, and we might be just making propellant that will allow the crew to get home. So that kind of power requirement, we're talking about 30 or 40 kilowatts. And then the crew arrives, and then they'll need power for their landers and their habitats and their life support and recharging their rovers. And so you can, bring another 30 or 40 kilowatts for that, or you can, kind of balance the needs and make ISRU propellant when the crew's not there and vice versa. The one thing that is probably true about these Mars missions is that the landers are going to be separated by maybe large distances to avoid plume damage. And so what that introduces is an interesting requirement to move power around on Mars. So let's say our power sources are landed on one lander, and 1 kilometer away our ISRU plant is located. Well, somehow we got to get the power there. And so there's concepts for cabling and beaming that might be candidates there. And like the moon, the Mars does introduce some real significant challenges on the environment. including a much lower amount of solar flux as what we see in Earth orbit or on the moon, plus large seasonal and geographical sunlight variation. So Mars has seasons, and with the seasons, the sunlight changes, and depending on where you are located, you might get some significant changes in that sunlight, not to mention the effects of dust storms and wind. So next slide, please. All right, this is a pretty complex slide, and I'm going to try and get through it quick, but it introduces a lot of important data in terms of contrasting these two mission environments. And it was really established, or developed, the table that is, to show the similarities and differences. And the first thing you'll notice at the top of the table is that in terms of power requirements, the Moon and Mars are pretty similar. Again, this is for those initial missions. In terms of the lander payload capability, for the Moon, we're talking about tens or maybe hundreds of kilograms for some of these commercial landers, and up to thousands of kilograms for cargo and human landing systems. Contrast that to Mars. So far, we've landed, hundreds of kilograms, maybe up to a metric ton. But for human missions, we're talking about the eventual need to land up to 20 metric tons. So big differences there in the lander payload limits, and that obviously drives the power sources. We already talked about power transmission distances, which I believe are going to be similar because of this need to land separately from previous landers to avoid plume damage. The Moon introduces a major requirement in terms of its maximum night duration, 354 hours of night for equatorial and mid-latitude missions. Even at the poles, we know that winter seasons will have night periods of 120 hours. On Mars, the night power periods aren't as long, but they do vary with latitude and season. And so it might be 12 and a half hours near the equator, but it'll be longer during the winter, especially as you go to northern latitudes. Already talked about solar flux, big difference there. At least half of the solar flux on Mars as you would experience on the Moon. And that varies significantly, as low as 100 watts per square meter, depending on whether you're in a dust storm. Gravity and pressure are key differences. The operating temperatures, the Moon is more severe with temperatures as low as 40 K in permanently shadowed regions. You have dust in both cases. In Mars, you also add wind, which complicates things. And because Mars is further away, we expect that it will require a greater amount of autonomy to make those systems work. But the main message, and this is the most important thing we need to take away from this session, I think, is that the systems we've flown to the Moon and Mars are a far cry from what we'll need when we start sending humans there. For the Moon, the longest power source we've operated is the ALSEP RTG, which was only 70 watts. And on Mars, the biggest system was the MER solar array, 140 watts, or the 110 watt Curiosity RTG. So we have a long way to go to get tens of kilowatts. Next slide, please. And I'm going to start to hurry up here because I know I'm probably running behind. I wanted to list some of the desired power system attributes as I see it. So rather than focus on solutions, what did the power systems need to do? We think they need to provide high power. We want them to last for a long time. We want them to have high reliability, certainly. These are powering crew systems. To the extent that they can, we want them to be multi-mission adaptable. In other words, systems that you could use on the Moon or Mars and maybe even up to the outer planets. Systems that would be usable for surface power applications and maybe even electric propulsion. We want our systems to survive extreme environments, and there are some real extremes out there that we need to consider. One of the ideas to also think about is novel uses and configurations. For ISRU, for example, you might want a power system that not only provides electricity, it might also need to provide heat. And so that's another aspect of the power system trade space that one needs to consider. And then affordability is certainly an important factor. We want to keep our design, development, test, and engineering costs low, our life cycle costs low, and to the extent that we can utilize commercial off-the-shelf components. I put last the mass, or the specific mass. And usually that's the first thing that power system engineers want to talk about. But in the case of lunar and Mars surface power, it's really the last thing, because there are so many more important factors in developing these technologies beyond their specific power, specific weight. Next slide, please. So STMB is focused on a couple of key technologies. There's a broad portfolio, probably a dozen different power projects that we have in work, but I wanted to focus on three specific ones. You've already heard a lot about nuclear power, and on the left-hand side is our fission surface power project, which we've just posted a RFI, a request for information, to explore technologies on. We're looking for a 10 kilowatt design that can be flown to the moon in the late 2020s. And that system would be not only usable on the moon, but extensible to Mars. And so we're looking forward to working with our industry partners and our DOE friends to develop that technology. Regenerative fuel cells is a really interesting technology, especially for the moon, where there are long lunar nights. Regen fuel cells offer a performance advantage over rechargeable batteries. And so we're looking at RFCs and also looking at things like leveraging propellant, residual propellant. If you have hydrogen and oxygen propulsion systems, those use obviously hydrogen and oxygen, as would the fuel cells. And so looking for ways to leverage the landers and have a common source of reactants for those power supplies. And then finally, large deployable solar arrays. And we've done this in space for decades, so we're pretty good at flying big solar arrays in space, evidenced by the space station and other things. But putting them on the moon or Mars and then deploying them, those are going to be some significant challenges and require some real technology innovation. So for the moon, we're looking at vertical deployed solar panels that would be located on the poles and high enough above the crater rims to access the permanent sunlight that occurs during the summer months, and then track the sun as it moves in the sky. And then perhaps we could leverage those same designs and use similar arrays on Mars. Obviously, they won't make as much power because there's less sunlight, and we would probably reconfigure them to be horizontal rather than vertical. But to the extent that we can, we'd like to leverage what we learn about lunar solar arrays to work on Mars. And my last slide, I think. Next. So my walk-off, lots of words. It's just basically saying all the things I've already said. We're definitely going to need a new generation of power sources for the moon and Mars. We want to have a sustainable presence, and it's going to require some real innovative options. And I think learning to live on the moon will really pave the way for Mars. And so those are keys, and we want to demonstrate as much as we can on the moon before going to Mars. The systems that will be needed, tens of kilowatts likely to power our habitats and our ISRU plants. Probably will be a diverse array of technologies, solar arrays and regen fuel cells, and maybe small fission power systems. And the bottom bullet really is about STMD. We put power and ISRU, for that matter, at the top of our priority list for technology development. We really see those as key technologies, and we're trying our best to invest in them to satisfy the needs of these future missions, but especially missions to the moon that will allow us one day to get to Mars. And with that, I'll conclude and turn it back to you, Larry.
Well, thanks, Lee. Thanks a lot to all the panelists. Really honored to have this team together. Glad you guys could take time out of your busy days to present. I think it's very good information. We did get a lot of questions, and unfortunately, we don't have a lot of time to respond. So possibly I'll get with Janet, and we will try to respond collectively to the questions. I want to make sure we get back. I just can't possibly handle all the questions. Just a couple quick ones. I want to ask, you mentioned about the RFI for FSP, fission surface power. The industry day, it was mentioned potentially there's 3 awards. The amount of money offered up for phase 1, which is 9 months, was I think 4 to 6 million, so let's say 5 million. So that my question to the panel is that realistic amount of money for phase one, given the goal would be to complete 30% of the PDR design for the engineering development unit by the end of phase one in 9 months. So on your question or answers, try to be quick and we can get more questions. So anybody want to respond to that?
I think it's pushing it a lot.
Yeah, I mean, if you think, we've talked, Lee and I have talked in the past how much it would cost to build a reactor. Some estimates are over $1 billion. Krusty kilopower experiment a few years ago was under 20, but that was a little different conditions. So if it's over $1 billion and you say, here's 5 million, go work this thing and get pretty well through your PDR, it seems like that's a real tough call. But okay, another question I have is, why is the moon a great proving ground for dynamic radioisotope power systems? Anybody want to respond to that?
So Larry, I didn't hear you. I think it's for me, but I didn't hear I only heard dynamic radioisotope power systems.
A great ground for DRPS.
Oh. Well, so the travel time to the moon is quick, right? So I'm not talking about trying to do a 9-year mission to get to the destination where I'm going to need the power. So that's one of the first aspects of it. And then so I can experience the whole cycle relatively quickly. And then the other is that the moon has the thermal cycles will be definitely a driver to prove out that that a system can handle a wide variety of environments. So that's another good reason.
Okay, very good. Thanks, June. I have another question relating to launch approvals. Should launch approvals be more streamlined or different for RTG type missions versus fission surface power reactors? Should we have a different approval process for the RTGs?
So I'll take that, and Lee and June and Ralph, feel free to jump in as well. So the current, the NSPM 20, the current launch approval process, which was just released last year, in a way moves away from this distinction between RPS and fission systems and sets up envelopes for radiation for the limit. So for example, the probability of an accident where X-REM, total effective dose, is released should be less than 1 in X. So that's so in a way it sets up these boundaries, which makes it much easier for a larger number of actors who'd like to be part of this ecosystem to develop innovative solutions, and they don't have to worry about. So it's not prescriptive. It just gives the boundaries, and I think that is the right way to go. It will encourage more innovation in the system, because what we really care about is exposing the public to high doses of radiation. It doesn't matter if it's an RPS or an FPS, but I think I know where the question is coming from. Radioisotope systems are plutonium-238, which has very high levels of radioactivity, and fission systems, at least at the time of launch, are going to be launched in essentially fresh, which means not a high level of radioactivity at all. So there is a huge difference, and so I know where the question is coming from. And I think the way the non-prescriptive way to address that issue is a better way to go. I don't know, Lee and June, do you have anything to add to that?
I thought you did a great job, Bhavya. I don't think I could add anything.
Yeah, that was good. I'd like to go to another question. So we talked about, my team once did a study for DARPA on the different radioisotopes, the pros and cons. And we always come back to plutonium-238. Does anybody want to comment on why that radioisotope is such a great radioisotope to use for RTGs? Anybody have any comments on that?
Well, I can take that, Larry. It's basically you can make it into a fuel form, the plutonium dioxide, which you can't dissolve in water. You've got an adequate lifetime. It's not too hot in terms of radiation background. So the workers that are actually assembling the systems can do that with a minimal amount of shielding. And yet at the same time, it's got a long enough of a lifetime, half-life of around 87 years, that combined with the converter technologies, you could do a multi-decadal mission. I mean, people have talked a lot about Americium-241. That's being pursued in Europe. Part of the problem is we don't have any separated Americium-241 here in the US because you have to do reprocessing of fuel, which we do not typically do. It is done in Europe. The power density is down by about a factor of 4, and there's a rather obnoxious, I think it's a 40 kilovolt gamma ray that you have to worry about for the people doing the assembly. So there's a lot of advantages, and people have, I mean, people have beaten on this day in and day out for about 40 years, and everybody keeps coming back to the same conclusion.
So if I could add to what Ralph said, I think the reason people keep coming back to the same issue is plutonium-238 is very, very expensive to produce. And it would be nice if there were alternatives. So, as Ralph said, 241 has some downsides, but if it's more cheaply available, and as it is in Europe, we know of at least 2 private companies that want to develop our radioisotope systems that are not based on plutonium-238. So I think there's a lot of interest in the community to look at alternatives, and it might be worthwhile for us to just keep our minds open to what alternatives come around, and as long as they meet some of these criteria, that would be good. I mean, I think plutonium-238 has an 87-year half-life, and that's great if you have these long-term missions going to the Kuiper Belt and beyond. But if you want, if you don't need the half-life to be that long, maybe you would want to consider some of these other isotopes these private entities are proposing. So it's pretty exciting.
Very good, Bob. I get the credit for both you and Ralph. It's 87.7 years, I believe. I think we had this discussion before, Ralph.
I got behind on the literature. Sorry, Larry.
So let me ask a question. We're talking about nuclear thermal propulsion, nuclear electric propulsion, fission surface power. Can NASA pay for all that? Is there enough money to go around to pay for all that? And if not, what are some of the alternatives?
Hey, Larry, I'll give a try at that one. So, no, I don't think we can afford all of them. And so we're going to have to make some decisions. But the good news is I think we can stage them in a way that they might be affordable. So I can see a future in which we develop this initial surface power reactor, say this 10 kilowatt system, fly to the moon, and use a similar one for Mars. And in parallel with developing that flight system, we developed the technology for nuclear propulsion. And I think we'd have to do some of that requisite technology development in parallel for both NEP and NTP. And I don't think it needs to be tremendously expensive to do the initial technology work. And I think given enough initial technology work, you could make an informed decision about one of them to pursue in earnest, in detail, with a significant investment that would enable those Mars missions that would come in the mid to late 2030s. And so I think NASA can afford all that. It just has to do it smartly, and it has to stage it correctly.
Very good, Lee. I appreciate that input. I think we have a couple minutes left. There were a couple questions relating to the conversion of the radiation into electricity. So you'd have another power source. Anybody want to comment on that, the possibility of converting radiation to electricity if you're on the surface of Mars?
Well, there is a radiation background which is more than humans like to be exposed to. But at the same time, if you actually look at the energy density, it's not that great. So I think if you do the numbers, it would turn out you would need such a large collecting area that somehow now I've got to process a lot of something to make collecting area, or I've got to bring a lot of mass with me. So I think making the numbers work is problematic.
Also, I think solar power is converting radiation into electricity, right? I mean, that's what that is. So we do that.
Well, we do that, but again, at Mars, even with solar arrays, if you're going to get up to the level of tens of kilowatts, as I think Lee was correctly pointing out, is if we're talking about human missions, you're going to have to look at something like that. You're talking about very large arrays, and I got to keep them cleared of dust, and et cetera, et cetera, et cetera. So I think a lot of practical problems, and which is why I think that nuclear power is enabling for humans on Mars.
Very good. I think, do I have time for one more question or not? I think I do. So this has to do with in situ resources on the moon. Do we know of any uranium deposits or in situ resources that would help facilitate nuclear power for our reactors or whatever we use on the moon?
I can jump in real quick. I mean, we did scans with a gamma ray spectrometer on the sub-satellites on Apollo 15 and 16. So we know where that there is uranium and there is thorium in the minerals on the moon. There are patterns. It's not just homogeneous. But that said, there's certainly no high-yield ore deposits like pitch blende deposits on the Earth we've been able to see from orbit.
Hey, Larry, that was a great answer, but I'd like to add to it in that even if there were uranium on the moon, the idea of making a reactor there is a tremendously complicated process. So we're not going to do that for our first reactor. Maybe we'll do it for our 10th or 100th reactor when we have a permanent human settlement going there. But yeah, even if there is uranium there, we're not likely to use it for any near-term reactor.
Okay, very good.
I was going to kind of make the same point. I mean, we know there is ice and water on the moon, and even there, I'm not 100% sure the business case closes for turning that into propellant at costs that are commercially viable necessarily. I mean, it's complicated, obviously. So to think that we can at zero cost extract the uranium and turn it into fuel quality material is a little bit optimistic.
Very good, panel. I want to say I think we've come to the end of time. I'm giving a few prompts to cut it off, so the hook is on me. But nevertheless, I want to thank everybody, including the audience, for stimulating questions. And we did have a lot of questions and a lot of folks listening in. So thanks to everybody. We appreciate it, and have a great conference. Thank you.
Thanks to you, Larry. Thanks. Bye-bye, everyone.
Bye.